Math 2415, Calculus 3, Multivariable Calculus, Chapter 10, Vectors and the Geometry of Space, Section 1, Three-Dimensional Coordinate Systems, Video 3, Projections. This is actually a really simple concept, despite the definition of what a projection is. A projection of an ordered triple ABC, so a point in three space, onto a coordinate plane. And remember, a coordinate plane is a plane that contains two of the three axes. So the XY plane, the floor, the XZ plane, or the YZ plane, two of the three walls. But a projection of an ordered triple ABC onto a coordinate plane is the point that has the same coordinates as ABC in the coordinates corresponding to the axes contained in the coordinate plane, but a coordinate of 0 in the third coordinate. In other words, in the coordinate corresponding to the axes not included in the coordinate plane. Fix that typo. Now, that sounds like a really tricky thing to do. It's actually really simple, as I'm going to illustrate. Defining it is one thing, but when you see the algebraic approach and the geometric approach, it's going to make sense. For example, we're going to find the projections of the point 4, -3, 2 into the following planes: the XY plane, the XZ plane, and the YZ plane. Let's process this definition real quick before we do this. To find a projection into a plane, let's highlight the important parts. We need the same coordinates in the coordinates corresponding to the axes contained in the coordinate plane. All right, so let's let that sink in on the first part. We are projecting onto the XY plane. The XY plane contains the X axis and the Y axis, which means our projection will have the same coordinates in the X coordinate and the Y coordinate. In other words, we're going to keep the XY coordinates. Now, what do we do with the other coordinate? Well, the other coordinate is a coordinate of 0 in the third coordinate. In other words, the coordinate corresponding to the axis not included in the coordinate plane. Well, the XY plane does not contain the Z axis, so we're going to put a 0 in the Z coordinate. So to put it simply, all we have to do is keep the X coordinate, keep the Y coordinate, and 0 out the other coordinate. So our answer would be real simple. Keep the X coordinate. That's supposed to be a larger font. Keep the Y coordinate, 0 out the other coordinate. There we go. So what do you think the projection of this point would be in the XZ plane? Well, in the projection into the XZ plane, we would keep the X coordinate and the Z coordinate and 0 out the other one. So we would keep the X, we would 0 out the Y, and we would keep the Z. So it'd be 4, 0, 2. And at this point, you're probably thinking, all right, this is easy. At least I hope you are. What about the projection into the YZ plane? Well, we would keep the Y and the Z coordinates and 0 out the X coordinate. So 0, -3, 2. So put simply, to project into a plane that's defined by 2 of the 3 axes, you keep 2 of the 3 coordinates and 0 out the third one. Well, that's cute and all, and algebraically or numerically speaking, it's actually pretty simple. But what does this mean geometrically? Well, let's take a look at it. Geometrically, the projection of a point onto a coordinate plane is the point you would get if you translated the point parallel to the x-axis, to the axis perpendicular to that plane until the point landed on that plane. And I meant to clarify what I meant by the word translate in the previous video when I talked about translating a line parallel to a certain axis. In terms of transformations, which in geometry is moving, flipping, and stretching objects, a translation is a movement of an object in a direction without changing its shape or its orientation. So no rotations, no stretches, we just slide stuff up and down. So the correct word for sliding an object without changing its shape or orientation is called a translation. So if you see the word translation or the verb translate, it just means to move something. So what does this mean? Well, to project onto a coordinate plane, you basically move the point to that coordinate plane in the direction parallel to the axis that's perpendicular to that plane. For example, the projection of the point 4, -3, 2 onto the xy plane was 4, -3, 0. That was the first one we did here. Now, you'll notice that I already have a picture of 4, -3, 2 illustrated. And I also want to mention something else about drawing a point in a coordinate plane when you're emphasizing how to get to that point. You'll notice I've got these three pinkish lines here that start at the origin and then travel in the x direction 4, in the y direction -3, and I know it travels in the correct distance because I actually drew this segment up here and then translated it down here, and then the z direction 2, which again I know is the correct distance because I took it here and translated this segment over there. And so that dot floating there is 4, -3, 2. Now, two-dimensionally, there are other 3D paths that would land at the exact same spot as this point, which is why it's kind of important to get a visual idea of how we got to that point representing these three line segments. And by the way, these three segments that are tracing out the path from the origin to the point that we wanted to find are called the traces of the point. This is the x trace, the y trace, and the z trace. Now, where's the projection? Well, the projection is 4, -3, 0. So it would have the same x trace and the y trace, but it wouldn't move up any. So that means that the projection is right here, because the coordinates of that would be, I'm getting everything set up here, coordinates of that point would be 4, -3, 0. Same x, same y, but I zeroed out the z coordinate. So what's the relationship between the original point, 4, -3, 2, and its projection onto the xy plane, 4, -3, 0? Well, it's almost as if this point right here, trying to grab it, it's not letting me grab it. 1 second, I have to make some adjustments here in order to grab that point. Move this over. Let's try it again. Grab that, still not letting me grab it. Okay, I'm going to move this over for a second. Grab that point, and we're going to move it down to the xy plane by zeroing out its z coordinate. In other words, we're going to translate this point parallel to the z-axis, because that z-axis is perpendicular to the xy plane, until that point lands on the xy plane. So it just drops down here. Basically, you just zero out a coordinate. I like to think of it as I'm taking a point that's floating in space and I'm squishing it to the floor if it's the xy plane, or I'm squishing it to one wall if it's the xz plane, or squishing it to another wall if it's the yz plane. Let's take a look at one more example from scratch. We're going to sketch the point 3, 3, -4 and its projection onto the yz plane. And I'm going to sketch it the same way that I did before by drawing the traces, starting at the origin and going the right direction, the right distance. So 3, 3, -4 means I would go 3 in the positive x direction, which is here. Then I would go 3 in the positive y direction, and I'm going to draw it up here, but then translate it down here. And we're going the positive y direction, which is to the right. And then 4 in the negative z direction. So it would go down 4, 1, 2, 3, 4, but it would go down 4 from here. And now we have this point down here that is the point of interest. The point of interest being 3, 3, -4. Let's put that in the same color. And let's bump the font size up a little bit. That's good enough. All right, so there's the point, but where is its projection onto the YZ plane? Well, the YZ plane is the wall in the background. It's this plane that contains the Y and the Z axis. So we need to take this point, which is currently in front of the YZ plane, and push it back. Now, we could do this algebraically first, but let's think about this from a geometric perspective. When you make a projection onto the YZ plane, you're going to zero out the X coordinate, which means we need to take this back. So I'm going to put that there and redraw it because I want the traces to be in place up here. But now think of it as taking this ordered triple and pushing it back 3 spaces onto the XY plane. Where would that put it? Well, if we're zeroing out the, if we are zeroing out the X coordinate, then the coordinate should be 0, 3, -4. And I want to verify that that is the correct one by tracing out the point 0, 3, -4 from the origin. We'll trace it out in orange. Why? Why not? Orange, please. So to get to the point 0, 3, -4, I would start at the origin, not move in the X direction, move 3 in the Y direction, which would be 1, 2, 3 this way. And then I would move -4 in the Z direction. -4 in the Z direction is this far. And if we take that trace and translate it over here, it kind of puts us exactly where we thought we were going to be. So that's the geometric idea of a projection onto a coordinate plane. You got this point floating in space, and somewhere you've got the YZ, the XY plane, the XZ plane, and the YZ plane. And you're taking this point and you're saying, you know what, I'm going to take that point and I'm going to smash you into the wall, smash you into the wall, or smash you into the floor by zeroing out the correct coordinate.